In this section I'm going to talk about pressure measurement and the different ways that we can measure the pressure of both liquids and gases. Okay, one of the simplest ways we can do this is simply with a piezometer tube. Okay, so if we have let's say this is a pipe which is running out of the page towards you. Okay, we can have this tube on top of the pipe. Okay, and in this instance it's open to atmosphere, so the gauge pressure here, okay, is measured at this plane x, which is along the centre line of this pipe, and so the gauge pressure is equal to rho g h. So the absolute pressure would obviously include the pressure due to atmosphere, but we don't want that. We want to know the gauge pressure because we're not really interested in that. We can take that out. However, if you did want to obviously know the absolute pressure, then you'd have to put that atmospheric pressure back in. So again, you need to get used to, in this context, so we can talk about pressure both in terms of pressure as in pascals, but also pressure heads, which has units which are measured in lengths or meters. Okay, this is a very simple way. However, if we wanted to measure the pressure of a gas, we couldn't do it that way. All the gas would obviously bubble out of our tube. So we need to trap it with what's called a manometer. So you can see in this instance we've got our gas pressure here, and the gas can't escape because we have this U-tube here and some liquid in here which is preventing this gas from escaping. Okay, so the gas is exerting a pressure on here. And as I say, this manometer traps it. And before I kind of come to the equations over here, I just want to kind of talk about this. You can really kind of have a guess at what the pressure is in here even before you start these problems, because let's say that these two fluid levels were at the same level, and we're obviously assuming everything's in equilibrium. If they were at the same level, then we know that the pressure here would be equal to the same pressure on this side, i.e. be atmospheric pressure, because the weight of the fluid would level out. So we can see here that because this side is lower than this side, this pressure must be greater than atmosphere, okay? Because if you think about it in sort of simple terms, it's pushing this fluid down, okay, against the atmosphere. So the pressure in here is above atmosphere. How much it's above the atmosphere would be the gauge pressure, which is rho g h. So whatever this liquid happens to be in here, you get the density, times it by g and times it by the h here. Okay, and if you wanted to get the absolute pressure, then again you'd have to add on the atmospheric pressure to the gauge pressure. And again, this is a pressure head and measured in meters, and the pressure head and pressure terms are interchangeable. However, you can see in this instance the fluid level on this side is higher than the fluid level on this side. Therefore, the pressure in here must be less than atmosphere, subatmospheric pressure. Okay, so when the pressure is subatmospheric, then the gauge pressure must be a negative value. Okay, because the absolute pressure is the pressure of the atmosphere. Because the absolute pressure is a gauge pressure plus the atmospheric pressure. If your gauge pressure is less than 0, then it means that you must have a negative gauge pressure. Okay, and in this instance, the pressure head is kind of referred to as a vacuum head. Okay, because you're sub-atmospheric. Obviously, the examples I've shown you there of manometers, they obviously used in labs and that kind of thing as a way of measuring pressure, but not particularly useful in industry. So there's a number of different gauges out there, and there's a good video here which explains two of the main methods. So again, I won't play the video, but here's a link for you to go and look at that. Sometimes you find that you've got more than one liquid in your manometer, and so if you've got two, they need to have two immiscible liquids, which means that they don't mix together, they separate. So if we consider this manometer with two immiscible liquids, then how can we work out the pressure on either side? Well, again, we can take, if you're quite clever in these problems, so one thing to just say, actually, most of these problems, half the battle is choosing a good datum. Once you've chosen a good datum for your problem, then it's quite easy to work the solution out. So the datum you'd normally take as the lowest change in a liquid level. So you can see that the paraffin's acting on here. This is the lowest change. And the reason for that is if you consider this bend, the pressure here must be the same as pressure here, otherwise it would move to equalize. So you can ignore all this bit from your calculations, okay? So if we consider our datum level, what we've got on the left-hand side of this manometer is we've got the atmospheric pressure and the hydrostatic pressure of the paraffin, okay, so rho GH of the paraffin. And what we have on the right-hand side is again, we've got atmospheric pressure and rho GH of the water, okay? So where these are at the datum, then we can equate the pressures, and in this instance the atmospheric pressure, the two atmospheric pressures would cancel, okay, so, and also gravity G would disappear, so we end up with the density of paraffin times the pressure head, which is equal to the density of water times the head here. And so you can see here that because water is denser than paraffin, it has a smaller pressure head compared to that of paraffin for the same hydrostatic pressure. Okay, so the example I showed you on the previous slide was a fairly simple example, and you'll see in this course there'll be more complicated examples. So what we really did there is the general equation for what we just did there is you can treat this as sort of a chain of hydrostatic pressures. So you start from one side, or you set what your final point is, okay, and what the pressures are is it's the initial point plus the sum of the hydrostatic pressures where you go down one of the tubes minus the hydrostatic pressure where you come up some of the tubes, okay? And so you can use this, if you remember this rule, you can pretty much solve any problem. One thing just to note is when you have liquids and gases, you obviously can't neglect the pressure of the gas, but you can neglect its hydrostatic pressure, because the density of gases are normally around 1,000 times less than the density of liquids. So you can neglect the hydrostatic pressure, but you still need to take into account the pressure of the gas. That's quite important. Okay, there's a video on here that I showed of kind of this in action using what's called Pythagoras's greedy cup. And he talks, there's a good professor in here who talks about the history behind this cup, but also how it works and how you could actually trick it by using fluids of liquids of different densities. So I'd really encourage looking at this. It's quite a neat video to watch, and it's explained really well. But if you don't have chance to look at that, then this is how it works. So the idea is that there's this cup, and you can fill it up with wine, but if you get too greedy and you fill it too high, then the whole thing runs out the hole in the middle and onto the floor. So how does it work? Well, obviously this is the empty cup, so we fill it up with wine, and in state B the pressure inside the manometer and the glass are equal, okay, so the wine would obviously sit there and not run out. But if you fill it up too far, then what you do is you force some of the fluid down here, around here, and that starts to run out. And so now you've got a condition here where the pressure in the glass here is larger than the pressure in this siphon in the middle. So it so because the pressure's higher, it'll force it out, and it'll continue to keep forcing it out till it gets down to the bottom and it uncovers this lip, and then the pressures will equalise again. So quite a nifty invention and quite a good demonstration of what we're talking about in this lecture. Okay, so that concludes this lecture, and thanks for listening.